Well, good morning, everyone. I think it's time for us to get started. So, we were, and still are, oops, let me adjust this a little bit. There we go. We were working on chapter 9, sampling distributions. We're going to focus today on sampling distribution of a proportion. Now, when they say that, they mean that your data is basically a percentage. So you asked us 100 people something, and 42% said yes to whatever your question was. So when you see a proportion, you are thinking like a survey or something where you ask people a question and 42% are going to vote Republican, or 12% are in favor of the death penalty, or I know 80% said they're married, whatever it might be. And we call them proportions. And the sampling distribution proportion was discovered that when you take a sample from a population and you take lots and lots of them, the shape of all the samples that you could have taken has a nice normal and distribution. It's a symmetric shape, just like this one. The mean of it, right here, will be the population proportion answer P. So in other words, that is, if you could ask everybody, that would be the percentage you said yes to your question. And the standard deviation of this distribution is P1 minus P over N, and N is your sample size. And so we're going to start today by doing some calculations where they tell us P and N, and they ask us to find these two. So one of the two questions is going to be really easy. So we'll start with, say, an example like question 1A. You're told the sample was 600 and that the population proportion was 50%. So 50% of the people like Pepsi Cola. And you're being asked to find the mean and the standard deviation. And this is why this is very simple. The mean is that guy. You don't even need to do a calculation. You just have to realize that the population P value, right, the population proportion value will be the mean of the standard distribution. Now, the standard deviation is the square root of P 1 minus P over N. And this will be 0.5, 1 take away 0.5, all over 600. So just go on the calculator, do a square root, put in the first number times the second number and divide by the sample size. And what we're rounding off to, 4 decimal places. So 0.0204. So if you can imagine what this might look like if you drew it, right in the center would be 0.5 and a standard deviation. Let's call that 0.2 just for easy calculation. It would look something like this. So that's what it would look like. And we're not doing any extra calculations on that. In fact, you're not even asked to draw this picture, but I chose to. So I'm going to show you something while we have this data. Let's suppose I didn't choose a sample size of 600, right? If I chose 600, This is the kind of shape that you would get from all your samples. Some would be a little bit bigger, some a little bit less, but most of them would be about 0.5. Same p-value, right? Same population, but this time we're going to take $6,000. Right, so if you take samples of size 6,000, the mean doesn't care how big the sample is. It's still going to be the population value 0.5. The standard deviation is the same formula, but the number in the bottom is going to be bigger. So here's my question. Will this new standard deviation be the same number as 0.02, bigger than 0.02, or smaller? What will it be?
Smaller.
Right, agreed. If you divide by a bigger number, your answer is going to be smaller. And just so we have a number to work with, let's find out how much smaller it truly is. So it's the square root of 0.5 times 0.5 divided by 6,000. And the answer we get is, I'm just going to call it 0.006. And if you sketched that second one, can you see that there'd be a lot less variation in your samples? Now, doesn't that kind of make sense? That if you have a very big sample, isn't the chances that it varies away from the middle a lot less, right? Which intuitively makes sense, right? Bigger samples, more accurate predictions, agreed? If you asked 4 people, couldn't the answer be all over the place? But if you asked 4,000 people, it would be tiny. And if it was America, I guess you could even ask 4 million people. But if you asked 4 million people, wouldn't the answer be a very skinny normal distribution with a standard deviation so small that you could probably bet your house that the answer you got was darn close to the population answer? And that's why we do samples. And that's why we try and do big samples. If you do a sample with a lot of people in it, you can be pretty sure whatever answer you get is going to be darn close to the real one. And if you can spend an awful lot of money, can you virtually guarantee it's going to be the same as the one you've got? Any questions so far? Right. Pretty much plug and chug. You got this formula. You're going to be asked to find the mean and standard deviation. So we've essentially done a version 1, just scanning through this. Question 2 is the same. Okay, what's different in question 3? Well, we're now going to look at sampling distribution, using the sample proportion, which is called p hat. If you think about it, the first couple of questions where you're actually told what the population proportion value is 0.5, it's quite unlikely, right? I mean, you might know it, but it's very rare. And if you did know it, these are just calculations. In real life, you don't know the population value. All you can do is find samples. And what does that sampling distribution look like? Well, it's normal. What do we know about it? Well, we know that its mean should be p, although now p is unknown. And we know that its standard deviation should be P, 1 minus P over N, right? But since P is unknown, what's the best we can do? Well, we can do P hat, right, the sample guy. And the standard deviation is P hat, 1 take away P hat over N. Would you agree if you don't know P, but you do know what the sample is, right? You took a sample and P was 0.4. Isn't the best you can do is the mean's probably close to 0.4 and the standard deviation would be this guy. So it's the same formula, but you notice it's not P's we're using, it's the sample number because we don't know P, right? In real life, we just know the sample. This fella is called the standard error. So standard error of P hat. And the standard error of P hat is another name for the standard deviation, right, of the sampling distribution, at least an estimate of it. Okay. Well, the kind of questions you're going to get are like this. This is question 3. A random sample of 500 drivers, 105, God, that's ridiculous, say they never wear their seatbelts. You tell me this is true. I think it's true. See people who drive around in post vehicles, I'm not sure, right? The mail vehicles, right? I don't think they need to wear seatbelts, do they? They still do? I can't remember. I'm just wondering why that is so high. I mean, maybe in some people's jobs they can get away with not wearing one. Right. So from this given information, we are being asked to find P hat, that's the sample proportion, and the standard error P hat, which is essentially the standard deviation. Well, P hat is basically what? 105 out of 500, which I believe is 0.21. And the standard error, well, it's going to be the square root of the P hat that we just found. 1 take away P hat over N. So 0.21. 1 take away P hat is what you get when you take this away from 1, which is 0.79. And N is the sample size. So square root 0.21 times 0.79 divided by 500. And they want the answer to 4 decimal places. So 0.0182. For all intents and purposes, isn't that the exact same questions 1 and 2? Aren't you just using a P hat where you used to use a P? So that one, because they're so similar, that tends to confuse people a little bit because they say, well, am I getting a standard deviation or am I getting a standard error? Am I getting a mean of the sampling distribution or am I getting a P hat? Well, the answer is you essentially, it depends if you know the proportion value P, in which case you're getting a mean and standard deviation, or if you only know what the sample is, in which case you're getting a P hat and a standard error. So, one's from a population, although they're similar, right? And one's from a sample. That's the only difference. So far, so good. Right, so that's question 3, looks like that. I'm just reading question 4. You have to read it because, oh, there we go. Question 4 is population numbers. Okay, let's use what we know here. Use this data. From this particular sample, we know that the p hat, which is essentially the mean, is 0.21. And I'm going to cheat a little because just for accuracy, I'm going to call that number 0.02. So that's to 2 decimal places. So that's just going to make my life a lot easier. I'm going to go 23, 25, 27. I'm going to go 19, 17, and 15. If you're wondering what's going on here, hold in just for a few more moments. This one here came from this sample, right? So we know that the mean is 21% and the standard error is, I've rounded off to 2%. I have built one of these guys. So there's the mean, 21, add 2%, add 2%, add 2%, take away 2, take away 2, take away 2. That's pretty much the normal picture that you've drawn lots of times, right? Now, this is the new stuff. 68% of samples. Aren't they going to fall in the range 19 to 23%? So in the range 19 to 23%. %95% of all the samples, aren't they going to fall within the range 17 to 25? Can anybody remember the ugly third one in this list?
99.7.
Now, if you turn this on its head, based on the one sample that we got, right, which is this guy, right? But the fact that we know that all the samples fall in this shape, couldn't we turn this on our heads and say, we're 68% sure the true answer for the entire population is in this range? We're 95% that the true answer will be in this range, and we're almost certain, 99.7% is almost certain, that the true answer, right, the P, the population one, is in this. So what we could say is, based on this sample of 500, we are 99.7% confident that the true answer for the entire population is somewhere between 15 and 27%, right, 0.15 to 0.27. That means that from one single sample, I can actually give you not just a prediction of what I think the answer is, 21%, but I can give you a range of where the real answer lives and how confident I'm going to be that it's in that range. Okay. So we are going to try that trick and see what we can come up with. So I am going to move to the whole screen, if I can hit the right button. And you lot are going to vote for me. So 2, 4, 5, 10, 15, 20. I'll make it 20, so I won't vote. So I'm going to do a sample of 20 people. And if you go to that little guy that has the, oh, why can't I find it now? You know the thing where you can stick your hand up and wave? I can't seem to say mine, but I know it's there. Should be in the bottom right-hand corner, shouldn't it? Right, David's found it. David, question. David?
Just testing it.
Oh, testing it. Okay, so that's testing it sign. Right, so I'm going to ask a question, and I'm going to let you, as a class, represent all of Olympic College. Right? You're a pretty reasonable combination of those students, and we're going to use this sample to make a prediction about what the entire population of Olympic College would think. So the question I'm going to put to you right now is, how many of you have actually watched at least 1 hour of the Olympics on TV? It can be spread over 3 visits, but you've watched at least 1 hour of the Olympics. Ooh, that's not good. Okay.
I couldn't find the little hint.
That's fine. I'm glad I got another vote because my data was going to look really warped because of that. So I'm glad that is there anybody else that couldn't find the little button? Right, anyway, there's definitely 2 of you. So I'm just moving my windows around so I can see what I'm doing now. So we have a sample in which 2 people said yes to my question. So that will make p hat, right, 2 out of 20. It's a nice number, right? 0.1. And that the standard error, which is basically a measure of how spread out you would expect the data to be, is going to be pretty massive, I think. It's going to be p hat, 1 take away p hat, all over n. So it's going to be the square root of 0.1, 0.9 divided by 20. Let's see what we get here. And the answer I get is about 7%. Okay. So if and it's going to be distorted, and I can't really do much about that. If we go right here, the answer is 0.1, and then that's 0.17, and that's 0.34, and that's 24, and this is 0.31. Right, well, that's a good point. If you go on this side, you get 0.03. Technically speaking, isn't there 2 more guys to the left? Would you agree? But would you agree that 0 is the lowest you can ever get for any kind of percentage question, right? Nobody watched it. So I'm going to have to lop it off there and stop at 0, right? So what can I say based on this? Well, I am 68% sure, right, that somewhere between 3% and 17% of Olympic College students have watched about an hour of the Olympics. If I move to the next one, which is what am I 95% sure, would we agree we just have to stop at 0, for common sense purposes? But it could be as high as 24. And if I go the 99.7, which is essentially, I'm certain, virtually certain what the right answer is going to be somewhere from 0 to 31%. Now, based on this tiny sample size, do you see how large the intervals are? It's almost like you're guessing. Yeah, the right answer is somewhere between 3 and 17%. But I'm only 2/3 sure that I'm right? There's a 32% chance it's bigger. When I get to this one, aren't we saying somewhere between nobody watched it, which isn't true because I know 2 people did, but almost nobody, all the way up to 31%. If this same sample was done with 200 students, and let's keep everything the same, you still got 10% of them. The standard error changes, its value changes. It's still 0.1 times 0.9, but now it's going to be divided by 200. And square root 0.1 times 0.9 divided by 200, and we get the answer 0.02. Isn't that a lot better than 7%, right? And the only difference really was the sample size, right? Do you notice the difference that asking 200 people does? You got this fella. So when I build my little guy, right in the middle is 10. And now we're going to go 2%, 2%, 2%, 2%, 2%, 2%. I'm going to write the answers here. 68 now is between 0.08 and 0.012. 95 is from 6% to 14%, and we're pretty much certain there's a zero there. And there were 99%, it's between 4 and 16%. Do you see the difference on making a much healthier sample size? Would you agree that these predictions are at least usable, right? Nothing to 31%, that's all over the place. You might as well say, well, I could have guessed that number, right? But now I know the real answer is between 4 and 16%. I've got a kind of understanding of what's going on. You sometimes take this guy. Let's take this one. You know, the one that was 0.1? And you add and subtract 3 standard deviations, in this case, 3 standard errors. What do you get? You get 3 times 0.2, you get 0.1, 0.2, plus or minus 0.06. You've probably heard the term that we use for this. They use it a lot when they do on the news. They tell you about surveys, or the latest poll. It's another name for a survey. Ever heard the term margin of error? And you always wondered, where did that plus or minus 3%, or in our case, plus or minus 6% came from? Can you see where it came from? It came from plus or minus 3 standard errors, right? That kind of, it's a kind of makes sense to me. So let's try another one. Since I'm in charge of the questions, we asked 1,000 people, it's a nice big sample. Are you going to vote for the Royalist Party in the coming elections, right? And we found out that 350, let's do 550 of them, because I want to win the election, said, yes, I'm going to vote for the Royalist Party. And that ends up being 55%, grade 0.55. Now, if you just used that data, couldn't you say, hey, the Royalist Party is going to win the Bremerton election? whatever it was, mayor's election, right? Right, 55% doesn't that win, right? In fact, doesn't 50% plus one person win, right? That's all you need to win an election. Well, if I calculate the standard error of p hat, see what it looks like. It's the square root of p, which is that number, times 1 minus p, which is that number, divided by 1,000. And the answer I get is 0.0. I'm going to round it off to 2 just to make my calculations easier, right? Then I'll build my usual guy that looks like that. Right in the middle is what my sample said. And then I'm going to add 2%, add 2%, add 2%. On the other side, I'm going to take away 2%, take away 2%, and finally take away 2%. And it's always the 99.71 that we choose. If you watch TV, they don't tell you they're choosing that one, but that's actually the one that they're choosing. To be real, it's a 99%, but we're doing the 99.7 right now. And that ends up being 3 standard deviations away from 9. So that's going to be p hat plus or minus 3 standard errors. And it was 55 plus or minus 3 times 0.02. So that's 55 plus or minus 0.06. And I'm going to turn this into percentages. So 55% were going to vote Royalist, and the margin of error was 6%. That ends up being 49% all the way up to 61%. So we are 99.7% confident that if everybody had been asked in Bremerton, are you going to vote for the Royalist Party, that it would be somewhere in the range 49 to 61%. And then I guess the most natural conclusion you would make then is this evidence that the Royalist Party is actually going to win the election? And unfortunately, the answer is no. It's too close to call. And the reason for that is that this interval is, we are 99.7% sure the real answer is somewhere in that range. But every single number in that range is just as likely to happen as any other, right? If 61% wins, don't they win by a landslide? But couldn't it also be 49%? And if it was 49%, didn't the other guy win? We'll assume it's a 2-party race. And so if sometimes you lose and sometimes you win, they use the phrase too close to call. So if you're into politics and you're watching the TV and the elections, you know, they've done an exit poll or they've counted some of the votes. You know, when they're counting the votes, aren't they just taking bigger and bigger samples, essentially, right, until everybody's voted? And they come up with this, and you wonder, how come the guy's got 53% of the vote, or in our case, 55% of the vote? How come he's done that? And you're still saying it's too close to call. Couldn't it finish up at 49%? Right, that's possible. Especially if you've only asked, say, the first 1,000 people, they're called exit polls, right? Who they were going to vote for. Any questions about that? So if you were wanting to collect good data, maybe you're working in a company, maybe you're an engineer and you've collected some information and you want to get a feel for what the real answer is, you could construct this process and it would be valid. And you could publish a paper and you could do it. Or you might read someone else's paper who's trying to convince you something is true, and you would look at it and you'd say, okay, how big was your sample? Oh, that's a good sample size. What was your 99.7 look like? Okay, you've convinced me. Or wait a minute, You could lose the election based on this, right? Well, let's just randomly pick a question then. Okay, this is question 7. Suppose the probability is P, so that's a population value, is 36%. So that's just a 36% chance that you win money. So you buy a lottery ticket, you know, one of those ones that pop out the machine, right? And you scratch them or something, right? You buy one of them, and there's a 36% chance you win your money. Do you know when you do that, isn't the money you almost always win is your stake? Like you bought a $1 ticket and you get a $1 back, right? So winning 36% of the time doesn't necessarily mean it's a good thing, right? But some lottery tickets are worth a lot more, I guess. Now consider a sample of 36, which could be that you're just a gambler and you bought 36 tickets, right? P hat is the sample proportion of the winning tickets in your sample. So P hat is essentially how many you won, right? Divided by 36. First question is, what would be the mean of the distribution? Wouldn't it be this guy here? Because we know that one. And what would be the standard deviation? Which I wish they would stick to calling it the same thing, but they keep calling it standard deviation. And then in the next question, they call it standard error. Well, we think of these as the same thing, right? They're just different names for it. And in this case, it's going to be P 1 minus P all over N. You only know one, right, or the other. So since I know this one, I can use it. 0.36, 0.64, all over 36. I think that should come out as a nice number. It looks like it might well be. Let's see. 0.36 times 0.64, all divided by 36 tickets. And it was a nice answer. They then go on and say, okay, find a 68%er, right? Now, if you want to do a 68, I could draw the picture and put all the little numbers in, but isn't the 68 going to be the P guy plus or minus 1 standard error? And 95% will be the P guy, sometimes P hat, plus or minus 2 standard errors. And if they want a 99.7%, it's going to be a P plus or minus 3 standard errors. So that's a bit like me going 1 standard error either side, 2 standard errors, 3 standard errors. And what one did they want again? They wanted the 68. Oh, and then they wanted the 95. Good. So you want the 68. It's going to be 0.36, give or take 0.8. And if you take away 1, you get on one side 0.24. And on the other side, you get 0.44. So there's a 68% chance that you are going to get between 0.24 of your tickets win and 0.44 of your tickets win. If you do 2 standard errors, it's going to be 0.136, give or take 2 of these, which is, this is 0.16. So it could be as low as 0.2, and it could be as high as 52. Okay. And if they wanted a 99.7, you could actually do that. The phrase that they use. This stuff here is called the empirical rule. It also has another name which I like much better, although it's uglier. It's called the 68, 95, 99.7 rule. Isn't that a much better rule, because at least you remember what you're meant to be doing, right? But if you see the word empirical rule, you're building these intervals up. So if I'm playing a game where there's a 36% chance I win something, right? Well, sometimes you win, right? Sometimes you don't. If you buy 36, right, tickets, then the chances, the percentage of those that win is somewhere between what, 0.2 and 0.52. So isn't there a chance more than half my tickets win? Can I get 51, 52%? On the other hand, couldn't I be really unlucky and only 20% of my tickets are winners? And if most of those winners are just getting my money back, you see that you'd lose a fair chunk of change if you did that. Although I have seen people buy lots of tickets, and I don't know why they think it's a good idea, because you know that the chances are against you winning, right? Unless you win the big one, right? 200 million. Any questions so far? You find these questions are very similar, because they are. I think for our last question for today, we'll do a guy called 8. It's got a lot of stuff in it, so here it goes. Suppose medical research thinks that the proportion of teenagers with high blood pressure right, so you're told that right now 70% of teenagers have high blood pressure. That's extremely high. But it would decrease if they took calcium sort of supplements. Oh, so you think it might decrease, do you? Okay. So they got a sample of 260. And the first question they ask us is, what would the mean? I'm just having to read through a whole load of stuff. And the standard deviation. Well, the mean would be 0.7, right? Because it's always that guy. And the standard deviation would be the square root of this guy. So it's going to be a 0.7, 0.3 over 260. And since I'm running short of time, I'll just tell you the answer, 0.0284. And that's what question A asks us. Now, question B wants us to do the 99.7 interval, right? So we're going to do the 3 standard deviation one. So it's going to be 3 plus or minus 3 standard deviations. Couldn't I call this P plus or minus 3 times standard error? Because they keep switching the names on us, although it's the same thing. Essentially the same thing. So what do I have? I have 0.7 plus or minus 3 of these guys. And that's going to be 0.7, add or take away whatever 3 times 0.0284 gets us, and that's 0.0852. This guy here would be called the margin of error. And the rounding off slightly different to 3 decimal places. You end up with that guy, and you get that guy. So far, so good. So if you took 260 normal high school students and you found out what percentage of that 260 had, you know, a blood pressure of that, the range that you would get from your sample would be somewhere between 61 and 78 of them percent would have high blood pressure. Now, in question C, they did a clinical trial with the calcium, and they want to see whether the calcium is doing a job, right? Did it make that go down? Well, let's see what we're told about this sample. There's 138 out of 260. So sample size is 260, and p hat is 138 out of 260. And 138 divided by 260 is 0.53 to 2 decimal places. Well, if I look at that, this is the normal population of high school students. These are the ones that took calcium, and then they measured their blood pressure maybe after 3 months or something. And would you agree it's definitely a decrease? So it looks like the calcium supplement does reduce blood pressure. But couldn't that just be a lucky coincidence that this is one of the small samples, right? Just happened to be, you know, you got a lot of people and, you know, they just had lower blood pressure. Now, this guy, is this a statistic or is this a parameter? What is the p hat here? So that's from yesterday's terminology. A statistic or a parameter?
Statistic.
Yeah, because it came from a sample. So it's statistic. And let's finish by making an assumption, or at least a conclusion. Would you agree that 53%, right, is lower than the range that you would typically expect from a sample size of 260? Isn't it living over here roughly? Right? Wouldn't you consider that strong evidence that taking calcium is in fact reducing your blood pressure? Agreed? Now, can we pretend a different story where they did the same thing, but the answer came back as 62%, right? 0.62. Isn't 0.62 in this range? So isn't 0.62 exactly one of the possible values that could easily have happened in this situation? So what we have built here is anything that happens in that range is not surprising. That's the kind of thing you would just get if you took a sample of 260. But anything that's outside this range isn't that significant. And in other words, evidence that whatever you're looking for is happening. Now, if the answer came out as 83%, wouldn't you be able to say, for God's sake, don't take calcium, it makes your blood pressure go higher, right? That would be evidence that it was a bad thing, right? So a more sophisticated version of this is how we prove in the statistics world, how we prove things. How do you prove that this new drug works? Well, you do something like this. How do you prove that somebody's going to win the next election? You create one of these intervals and you find out what, you know, whether everybody's bigger than 50 or not. And say your last name, everybody, because that is us for today.